I'd like to do a little perspectivization to put linear regression, simple linear regression, into perspective a little bit, with the focus towards extending. You would sort of call it extended regression modeling, since this is a very general tool for us in statistics and in modeling in general. 3 things I'm going to focus on here. I'm going to focus on multiple x's. I'm going to focus on nonlinearity. And I'm going to focus on sort of categorical, or maybe quantitative but non-normal observations. Whys. These are 3 very important things where sort of our classical regression, simple XY regression, in a way breaks down. It's not enough, but we can still do regression modeling in these generalized situations. The multiple case, A, B, C. The multiple case, usually called multiple linear regression, MLR, is an approach where we can look at observations y not only as a function, here's one way of putting it, of 1 x, as we have done now in the simple regression, but actually there could be several x's, more than 1 x, to x2i up to maybe xpi, like this. There could be p of those and not only 1. There could be several explanatory variables here. Now, this can be dealt with, actually, exactly similar to what you have now learned for basic simple regression. Actually, and of course this is just a hint about what we can do here. The first thing would be to try to find out how to compute all the b's. And we put such a model can actually be put into matrix vector form like this, in which we have an n by p. We would then call it a design matrix very often. We would have a vector of unknown betas, and we will have a vector of residuals like this. Having put this into matrix vector form, there is a general way, and the least squares regression estimation can be solved also in this multiple x case, actually. And I'm not going to do it now, but it can be solved in this multidimensional case. And the solution can be expressed in terms of matrices as x transposed x to the minus first, x transposed y. This would be the formula for computing all the b's. There's a simple formula, which, if there's only 1 x, boils down to our simple formulas for a and b that we've seen. And also, the theory will give us that we know the uncertainty about this, since we can compute SE squared. In this case, it's not n minus 2, but n minus p minus 1. It's the usual sum, actually, I equal 1 to n, yi minus, let me just in brief then call it yi hat. That would be the predicted value of this kind of plane formula given from up here. And then the uncertainty about these parameters would be given by this one times the inverse of x prime x matrix. So based on this, we can do hypothesis testing, confidence intervals, prediction, confidence intervals for the plane, whatever can be expressed here, just as in a single x case. So now we can build up models with multiple x's for predicting or modeling y. One big issue then is to think about the interpretation of the individual b's. Now, if there's only a single b, it's just a slope in a line. That is the interpretation as we are used to. If there are more than one x in play, the interpretation of the individual b is kind of everything else being the same, kind of economic point of view, that it's the effect on y of the individual x, keeping all the other x's fixed at their at a fixed value. So it's the individual unique effect of the individual x. That does put some requirements to the need of being able to have unique information about the individual x's. So the MLR becomes a bit not so good if we have many x's that sort of compete in telling the same story, you could say. That is a whole kind of extension of the MLR on its own into so-called multivariate prediction techniques. I'll skip that completely here. Just wanted to mention that an important point for this generalization, in R, the function LM, which I mentioned for simple regression, can easily handle multiple x's. Exactly, just adding the x's to the model. This is quite nice, actually. So that was the multiple linear regression extension. The second extension was, what about when structures are really nonlinear, either in a single x or in multiple x's, actually? How can we cope with that? Let's focus on a single x. Well, nonlinearity. I mean, what if y actually depends somehow on x in a nonlinear way? Could we estimate this? Yes, we can. One approach would be to use what I've just learned you about multiple linear regression, is to use MLR with polynomials. That is, we call that polynomial regression sometimes. That is, you may add an x squared term, you may add even an x cubed term, you may add different. And even if you have more than one x, you could also add x1 times x2 or x1 times x2 squared. You could sort of add all sorts of polynomial combinations to the modeling. And in this way, be able, this is interesting actually, be able to model nonlinear patterns by what is actually linear models, because it's still a multiple linear regression model. You just put in nonlinear values in a way, in a linear way. You could think about that. So you could deal with nonlinearity structures still with what is, mathematically speaking, still linear models by so-called polynomial regression models. That would be one approach. Actually, you could be more generic nonlinear and go for what is known as nonlinear regression approach. And I should say right away, in R, there is an NLS function to be used for nonlinear regression. Nonlinear regression is another sort of very straightforward generalization of simple linear regression. It's a way where you express the model, where you have some kind of nonlinear function as a model, how y depends on x, not through a linear model, but through a nonlinear model. It could be an exponential or a combination of exponential within, like in chemistry. And it depends, of course, on the input x, and then it may depend on some unknown parameters. I use theta underscore here to say this is what in a linear setting would be a and b, or alpha and beta. Now it could be different things. There could be one, there could be many such thetas. If we then assume still, for instance, that we have a normal distribution, the nonlinear regression could be solved by the least squares criterion, or what then also amounts to maximum likelihood actually, since we could look for trying to minimize the sum of squared deviances like this. So we minimize this, so sum up to n of course, we minimize this least squares criterion. This usually needs computer power, since this is a nonlinear function minimization, and very often this will not have analytical solution. But that doesn't really matter. If we can solve it by the computer, then we can still find the solutions, but without having analytical expressions for that. And so this would give least squares or maximum likelihood estimates of theta, and then we can go on and do, I mean, this would be assuming the normal and least squares would be the same. You could add other distributions actually and do maximum likelihood nonlinear regression with other distributions. And then you could go on, do hypothesis testing, confidence intervals, whatever, still within a truly nonlinear model. Finally, I was gonna mention a third thing, and that would be, what if our data y cannot be assumed to be normally distributed? What if it's not even quantitative? What if it's some kind of categorical? What if it's just even a binary thing, like throwing a coin or something like that? So that would be, what about models for categorical data? Say, categorical data. Could be maybe binomial outcomes, as I mentioned, or maybe Poisson outcomes where we count something, but still we might have an interest in doing some kind of regression modeling, at least between the means of y and some underlying x. And typically, for instance, if we have a binomial, let me just indicate, we would have that yi would be either 0 or 1, that is a binomial with 1 and pi. The way you would express the model, actually the pi here is then the expected value of yi. So now regression models for binary outcomes like this would not be expressed as a direct link between the observation and the x input. However, some nonlinear function, for instance, what is known as the logit, is used. So the log of this odds, you could also call it pi divided by 1 minus p. This is the sort of the level. This, you put in some nonlinear link, actually, a nonlinear function. This is where you could, for instance, express even a multiple linear regression, actually, if you wanted to. You could have 2 there. So you could express regression models, x2i, on a sort of nonlinear scale, or at least having a nonlinear link between the linear scale and the expected value of the observations. And then if you, for instance, had Poisson data, there could be kind of log linear model coming up out of this. And all of this together, I mean, this type of extended modeling, I'm giving to you very brief, you can find books about that. That is known as generalized linear models. Generalized linear models. And for instance, in R, you will find a procedure called GLM for generalized linear models that can deal with regression models for quite a large number of type of outcomes, actually. So, and these were 3 very important extensions that shows you that regression modeling is really something that can take us very far, at least if we allow us to extend it a little bit into multiple inputs, nonlinear approaches, or even normal, even non-quantitative outcomes. All of these things can be put into extended regression models, and there are procedures and theories and methods for us out there to dig into it. So you can do it, or you can take some more classes to learn more details. This was just a few minutes sketch of what is out there. Thank you.